Welcome to Brain Vision.
In this question, we want to find the number of atoms that there are in different energy states. And we're going to use the Boltzmann's distribution equation, that is, the number of atoms in a particular energy is equals to the total population multiplied by exponential negative E over kBT, right? Where kB is the Boltzmann's constant, T is our temperature, right, in terms of kelvins. So what we want to find is the ratio between the 2p3 over 2 state as well over the 2p 1 over 2 state, 2p half. So what we'll need is basically the energies of that level, because if we were to divide this expression, the only difference would be the energy, right? We already have, and the n total population will cancel out. Right? Basically, this. I'm gonna just call this 3 over 2, right? Because it's 2p 3 over 2 divided by kBT. Right, this total population cancels out. What we get is just E power of E half minus E 3 over 2 divided by kBT. So what we need is to find what is the energy of this, the energy difference between these two states. And the way that we're going to do that is by looking at the photons that are being emitted, right? We are given that the wavelengths of the photons emitted from each of these excited states, right? So we can actually find what is the energy of this based on the photon that is being emitted. So it's be 8c over lambda 2 from the figure. The wavelength of the photon being emitted is 5.896 times 10 power minus 7 meters. This will give us 3.369 times 10 to the power minus 19 joules. But we do the same for the 3 over 2, right, 2p 3 over 2, except that the lambda, the wavelength that we're going to use, is 5.89 times 10 power minus 7. And this should give us about 3.373 times 10 power minus 19. Therefore, we can actually find the difference right. We want to take half minus the 3 over 2, which we should get about 4 negative 4.0 times 10 power minus 22 joules. Substituting in to our ratio that we need, right? The ratio is just the exponential to this energy difference, which is negative 4 times 10 power minus 22 divided by kBt, so we're getting Boltzmann's constant, multiplied by the temperature, which is 500 kelvins. And we should get a ratio of about 0.944. And this tells us that, right, our more atoms are in the 2p half state, right? Because this is 2p 3 over 2 over 2p half, and since this is less than 1, it means that, right, this value is smaller than the number of atoms in the 2p half state. So there's more atoms in the 2p half state at 500 kelvins.